do a nice little problem. Involving, well, we got an incline, we got a spring, we got a mass, we got some friction. Ooh, this is gonna be crazy. Nah, not really. All right, so here's the scenario. We're gonna take a mass of 3 kilograms and we're gonna put it 2 meters up an incline of 50 degrees. And we're gonna release that mass from rest. It's just gonna slide down the incline 2 meters, and it's gonna slide across the level ground for 0.25 meters. Then it's gonna contact a spring that has a spring constant of 700 newtons per meter. And we wanna know by how much does that spring compress in bringing the mass to rest. Briefly, and then shoot it back up. But nonetheless, that's what we're asking. So first, we're gonna look at this as being a conservative system in which friction doesn't act, and then part B, throw friction in there and see what there is to be seen. So, part A, frictionless. Frictionless surfaces. Well, if there's no friction, then let's think about what's gonna happen. We are gonna have that this mass just slides down under the action of what? The gravitational force, which is a conservative force, right? Good. So a conservative force is gonna act on this mass while it slides down, increasing its kinetic energy at the expense of gravitational potential energy. And once that's all converted into kinetic energy, then it's going to slide across the level ground. When it's sliding across the level ground, if there's no friction, then what? There's no change in energy, so there's not going to be any change in energy right in here. It's just going to continue sliding with whatever velocity or speed that it reached the bottom with, and then it's going to contact the spring. Well, the spring force is a conservative force, and what's going to happen? When it reaches the spring, it'll have a certain amount of kinetic energy, and it will reduce that kinetic energy in compressing the spring, increasing the potential energy of the spring until all of the kinetic energy of the mass is gone, and everything's potential in terms of being stored in the spring. So, ultimately, frictionless surfaces, this is a conservative system. So we can approach this very, very simplistically, because whatever energy this mass has in this state right here will all be converted to kinetic energy, and then that kinetic energy will all be converted back into spring potential energy. So really, whatever energy it has here in terms of gravitational potential energy will be converted into spring potential energy here. Whew, that seems pretty nice, right? So we've got delta PE sub G will go to delta KE, not saying they're equal, saying that the gravitational potential energy will be transformed into kinetic energy, and then the kinetic energy will be transformed back into the spring potential energy. So, what does this ultimately say? We don't even need to figure out anything about the kinetic energy of the system. We just skip it out, because this goes to this, goes back to that. So, we've got the change in gravitational potential energy will be equal to the change in, no, I shouldn't say equal to, we'll go to the change in spring potential energy. So the reason I don't want to say is equal to, because we are losing gravitational potential energy and we will be gaining spring potential energy. And that's pretty much that. So whatever is lost in gravitational is gained in spring potential. So we can go ahead and say delta PE sub G is going to be equal to negative delta PE sub S. Because it's a conversion, one to the other. One loses, the other gains. This is going to end up being negative, but we could go ahead and write this out. Delta PE sub G is mg delta Y. And delta PE sub S, well, we're going to put a negative sign there and say that that is PE sub S final minus PE sub S initial. Well, let's expand this out a little bit and note something. what is the initial potential energy stored in the spring if it's not compressed? X initial is equal to 0, so PES initial is equal to 0. This term right there, whoop, is equal to 0. So what do we get? We've got ourselves that mg delta y will be equal to negative PE sub s final, which we can then write as mg delta y is equal to negative 1/2 kx final squared. Now that negative sign may be bothering you, saying, oh, well, it's going to have negative energy? I thought it was gaining potential energy. Remember here, delta y is actually going to be a negative quantity because we are going from a higher elevation to a lower elevation. So we're losing gravitational potential energy. This will end up being negative, equals this negative, which will give us next to this positive as it should be. So let us go ahead and figure out what we need to figure out. We're trying to solve this for x final. We need to know what k is, which we know, the mass, which we know, the gravitational acceleration, which we know, delta y, we need to know that. This is not delta y. That is the distance that it slides along the incline itself. Delta y is that distance right there. There's delta y. So how are we going to get delta y? We use a little bit of trig, right? We've got the sine of 50 degrees as delta y over 2. Thus, delta y is equal to 2 times the sine of 50 degrees. But again, we got to make sure that we're interpreting this correctly in terms of changes in gravitational potential energy. So this is a negative, and that's 2 meters there. So again, we got to kind of put that in there because of how we interpret changes in gravitational potential energy. So in the end, what do we have here? Well, from this, we've got ourselves, let's just put the negative sign in. Let's just do this. We can write ourselves that m times g times negative 2 times the sine of 50 degrees. That's our mg delta y is equal to negative 1/2 k x final squared. Good, good. And then we want to solve this out for x final. So we can multiply both sides by negative 2. This becomes just a positive 4. Divide by k, take the square root, and we've got ourselves that x final is going to be equal to the square root of, I'm going to move this out there, again times negative 2, it's going to be 4 mg times the sine of 50 degrees divided by k. Okay, that seems easy enough. So we got that it is 4 times 3 kilograms times g times the sine of 50 degrees divided by 700 newtons per meter. All right, what do we end up getting with this? Drum roll, right? Here we go. Square root. Times the sine of 50 divided by 700. We get 0.35874. 0.3587 meters. 35.87 centimeters. Well, we got to assume that the spring can be compressed by that much, but that's what we get there. 12. Yep, that sounds good. All right, so here we go. Fairly straightforward with respect to it being a conservative system. Now let's complicate things a little bit and look at the case where we throw in some friction and say that the coefficient of friction is 0.275. B, not frictionless. So we're going to say for both the incline and that horizontal surface that the coefficient of a kinetic friction is 0.275, excuse me. All right, so let us look back at this because we've got to be a little bit more careful now. So it's going to slide down this incline, right? Changing its gravitational potential energy, losing gravitational potential energy, gaining kinetic energy, but also losing some energy to friction. So we got three things in play there. We got the gravitational force, we got the force of friction, and then we've got the correlation with energy and changes in kinetic energy. So there's one thing going on. Then we got this little bit right here. Well, this little bit, we have no gravitational force affecting the object, just friction. So in this case, only friction is really doing any work. And then once it reaches the spring, we've got the spring force and the force of friction both doing work. So we got a change in spring potential energy and work done by friction, which will result in a change in kinetic energy. So this really resolves down into three different systems. Putting it all together at once gets really messy really quick. So in cases like this where we have transitions from different forces acting over different portions, it's best to just take one system at a time, link them together, and then figure out what the end result is. That's my opinion. You can do it all at once, but it gets messy really quick. So, erase this part right here, because we're going to need some room. I'll leave that result up just for a comparative aspect. And we'll go ahead and see what to do. So first, it slides down the incline. We've got a release of potential energy. We've got friction taking away some energy, and we've got some kinetic energy being increased. So let's do this all with energy considerations. That's the topic here, and go from there. So we've got ourselves the delta PE sub G plus delta KE has to be equal to the work done by the non-conservative forces, which is just friction in this case. So work done by a kinetic friction. So we can figure out what this is. This is our mg delta y. This is our 1/2 mv final squared minus 1/2 mv initial squared. And that has to be equal to the work done by friction, which we should already kind of have a good grasp at. Let's write this out formally. We've got ourselves F sub k hat dot delta r hat. Delta r hat is ultimately this 2 meters down the incline, and the force of friction is up the incline. So we should note that there is a negative sign between these two. And then we got to be a little bit careful with the force of friction here. So let us write out this. The work done by F sub k can be written as F sub k delta r times the cosine of theta F sub k. Theta F sub k is going to be equal to 180 degrees, as it always is, which gives us the work done by kinetic friction in this case being equal to, well, we know that F sub k in general is mu k times n, so we can write this as negative mu k n delta r. That's good. But what we got to be really careful of is what is n in this case. Well, if we go back and think about inclines, the only thing pushing down against the incline is the mass due to the perpendicular component of the gravitational force. Thus, the normal force has to be equivalent to that in its magnitude. We've got the normal force magnitude is equal to mg times the cosine of theta sub I, where theta sub I is the angle of inclination here. So we've got to be a little bit careful because there's some different thetas floating around. But this is what we've got. So in the end, what do we have with the work done by kinetic friction as it slides down the incline? The work done by kinetic friction is going to be equal to negative mu k mg cosine theta sub I times delta r. Again, delta r is just the 2 meter distance that it slides down the incline. All right, Well, let's go ahead and put that in here and see. We've got ourselves mg delta y plus 1/2 mv final squared. Go ahead and do one thing here. We also know that this mass was initially at rest, so this term is equal to 0 there. Let's get rid of it, make this a little bit more manageable. And then we've got ourselves negative mu k mg cosine theta sub I multiplied by a delta r. There we go. So what do we really want to figure out here? It's a good question, right? What are we solving for? Well, we are solving for ultimately this right here. How much kinetic energy does this object have when it reaches the bottom? We could figure out its speed, that's fine too, but it's going to be preferable just to figure out the kinetic energy. So let's expand on that a little bit. We've got that both the gravitational force and the force of kinetic friction are doing work, and that results in a certain change in kinetic energy by the time it reaches here. Then across this distance, we'll have friction doing work, which will result in a certain amount of kinetic energy here, which will be less than what it had here. But it's going to reach here, reach the spring with a certain amount of kinetic energy. So then whatever kinetic energy it reaches the spring with will be converted into spring potential energy, and some will be taken away by friction, because friction will continue doing some work as well. So really the end game here, in terms of getting to the spring, is to figure out how much kinetic energy does it have when it reaches the spring. If we can figure that out, then we can apply conservative, non-conservative forces acting with just the spring system and go from there. So let us figure out what this term is right here. KE final. That's it. So we want KE final. Well, let's just solve for it. We've got KE final is equal to the 1/2 mv final squared, which is going to be equal to negative mu k mg cosine theta sub I delta r minus mg delta y. Throw that over on the other side. There we go. All right, so I'm not going to solve this for v. I'm going to solve this for this whole thing. So this is really the quantity that we want right here. Let us go ahead and quantify this out then. Change colors here. This is getting a little inundated. It's okay. We've got the KE final is then equal to negative 0.275. Is that what we said? Yes. 0.275 times the mass of 3 kilograms times g times the cosine of 50 degrees times 2 meters minus 3 kilograms times g times delta y. Well, again, this is delta y right here. Negative 2 times the sine of 50. That is the change in elevation made negative because it is descending, and thus we've got ourselves a little bit more room there. Multiplied by negative 2 meters times the sine of 50 degrees. All right, that looks pretty big, but it's just some little quantities there. Let's go ahead and throw this in and see what this turns out to be. We've got ourselves negative 0.275. 3.8 times the cosine 50 times 2. 3 times 9.8 times 2 times the sine of 50. If we put all that in right, yeah, we get ourselves 34.6495. 34.6495 what? What are we solving for? The final kinetic energy. This is the number of joules of kinetic energy that this object has upon reaching the bottom. can we make sure that we got something that seems at least within the realms of reason? Well, what we could do is we could calculate what the initial potential energy was, or the change in potential energy that it went through, the mg delta y, compared to this. So let's just do the mg delta y really quick. We got m times g times delta y, which was 2 times the sine of 50. And putting in bad quantity there, 3 times, 1.8 times 2 times sine of 50. And we end up with the change in potential energy was actually negative 45.0434. So we lost about 45 joules of potential energy, but we only got back 34.6 joules of kinetic energy. Why? Because friction took some energy away, about 10 joules or so. So this makes sense. This seems reasonable, and again, trying to make sense of stuff, make it real, and feel for it. Friction took some energy away, great. All of the potential didn't get converted into kinetic. There's what we got. So that's a part of the problem, right? Well, we're not there yet, but we're almost to the spring. Now we've got the second part. This mass travels along the horizontal surface for a distance of 0.25 meters. So now, second, mass travels 0.25 meters along the horizontal section. So what do we have there? Well, there's its initial kinetic energy, and it's going to have some final kinetic energy. We've got the only thing doing work here. The net work done is equal to the work done by friction in this case, which will result in the change in kinetic energy of the system. Our initial kinetic energy is equal to this, 34.6495 joules. We want to figure out what KE final is. Well, just consider the work done by friction, excuse me. We've got ourselves this. The work done by friction over this section is going to be equal to negative, should we put it all? We know what it is. It's negative mu k mg delta x. The negative sign is doing negative work. Mu k times n times the displacement. That will be equal to KE final minus KE initial. There we go. So we want to solve this out for KE final. Let's just do that. Look at ourselves that KE final is going to be equal to KE initial, whatever initial kinetic energy it had, minus the work that friction did, mu k mg delta x. So with this, we can go ahead and put in what we know. We got KE final is going to be equal to 34.6495 joules minus 0.275 times 3 kilograms times G times 0.25 meters. And we get a final kinetic energy of 34.645. $32.62825. Okay, final is 32.82625 joules. So friction took a little bit of energy away, not a whole bunch, but it was only over a 0.25 meter distance that friction acted. So there we go. So now it reaches the spring with this much kinetic energy. So now we're finally at the spring. So we can go ahead and do a lastly, if you will. At the spring, we're going to have kinetic energy being reduced. We're going to have spring potential energy being increased, and we're going to have friction continues to act, taking away some energy. So now we go back to energy considerations with both conservative and non-conservative forces acting, and we've got ourselves delta PE sub S plus delta KE is equal to the work done by friction. All right, so we already know what the change in kinetic energy is going to be. It's going to go from this initially to 0. So it's really going to be negative that. Change in potential energy, well, let's just write all this stuff out, shall we? Let's do this. We've got ourselves. This can be written as a 1/2 kx final squared minus 1/2 kx initial squared plus ke final minus ke initial. I'm just going to break that open like that. And that has to be equal to the work done by friction. Well, the work done by friction is going to be negative mu k mg delta x. Horizontal surface, and it's just mg, negative because it's always doing negative work, and there's the distance that it moves. So let's note some things. We have that the initial state of the spring it's at equilibrium, so x initial is equal to 0. It's equal to 0, so the initial potential energy of the spring is equal to 0. So that leaves us with this. We've got the final kinetic energy of the system is going to be equal to 0 because V final is going to be equal to 0 because the spring is being brought, the mass is being brought to rest. And what else do we have? Well, we've got this delta x here. What's delta x going to be? Well, delta x is the distance over which friction is acting, which is going to be equivalent to the distance that the spring becomes compressed. We have that delta x is equal to x final. The spring becomes compressed from 0 to x final. That's the distance over which friction acts on the mass while it's in contact with the spring. So hey, that's what we're solving for, so that's nice. So let's go ahead, put in the KE initial. KE initial is actually equal to this. This was the energy that it reaches the spring with. So we've got 32.82625 joules. And we can go ahead and solve this out at this point. Putting in some values here. So let's move some stuff around a little bit. Clean this up. Got 1/2 k x final squared, that's 0, that's 0. Then we got minus 32.82625 joules, which has to be equal to negative mu k mg. And now I'm going to substitute that delta x for x final again, because that's what we're trying to solve for here. Now look at this. We've got a quadratic term in x, a linear term in x, and it's not adding up to be equal to 0. Uh-oh, let's see what we got. So I'm going to take this term. Actually, I don't even want to throw it on the other side. It's not going to really do as much good. We'll just put everything on one side, shall we? So we can write this as 1/2 k x final squared plus uk mg x final minus 32.82625 joules is equal to 0. Why do I want to write it like that? Because we've got an ax squared plus bx plus c is equal to a 0. So let us get these terms here. K times 1/2, that's going to be 350. So we've got 350 x final squared plus, let me compute that out really quick. We've got ourselves 0.275 times 3 times 9.8. That's going to be 8.085. X final minus 32.82625 joules is equal to 0. I'm leaving the units off of these. I should just take it out. So what do we get? We get an ax squared plus bx plus c is equal to 0. Ax squared plus bx plus c is equal to 0. Hey, quadratic solve. So let's just go ahead and do that. We've got ourselves quadratic formula. We've got the x final is going to be equal to opposite of b plus or minus the square root of b squared minus 4 ac all over 2a. We've got the a is equal to 350, b is equal to 8.085, and c is equal to negative 32.82625. And what do we do? Stick it in the calculator, right? Solve it on out. Luckily, I've got the quadratic formula already programmed in here, so that makes things a little bit easier for me. You stick it in, 350, 8.085, negative 32.82625, and kaboom! I get two answers, one that is correct and one that is incorrect. The correct answer is positive 0.2949. 0.2949, and that will be meters. Correct answer. There's another answer. We get to one for the plus, one for the minus. The wrong answer is the negative one. X final can't be negative. Why not? Because it's a positive quantity. It's how much it's been stretched or compressed by relative to the equilibrium position. It is a positive quantity itself. So that's basically that. The negative answer mathematically is possible, but physically has no sense attached to it. So that's it. Spring compresses by about 29.49 centimeters or 0.2949 meters. Compared to when friction did not act, it compressed by substantially more, right? Because friction didn't take away the energy. Friction takes away some energy, there's not as much left over for the spring potential energy to store it. And that's pretty much that. All right, that was fun, right? Good problem, good times. What else can you do with this? This is the problem that you can keep going on and on with, because now the spring's compressed by 0.2949 meters. What's it going to do? Whoop, the mass comes to a stop briefly, and then boom, the spring pushes it. And what's it going to do? It's going to go up the incline. How high up the incline is it going to go? Well, if friction continues to act, it's definitely not going to go 2 meters up the incline. It's going to go substantially less. And what's going to happen? It's going to go up the incline to the maximum amount, slide back down, reach the spring. The spring is going to become compressed again, but not by the same amount, because friction continues to extract or take away mechanical energy from the system until eventually the mass comes to a stop. Friction takes away all the energy and there's nothing left. We can think about, well, how many oscillations take place? How many times does it go up and down the incline before that happens? And that'd be something that would be a great exam type of a question, wouldn't it? I agree. All right, well, that's that. Have a good one. Until next.